So welcome to the first video for Chapter 2, Section 6, which is on rational functions. This is just going to be a brief video on the definition and then on end behavior of these functions. So in general, a rational function, it's going to involve a fraction, and it's just a polynomial divided by another polynomial. So I'd say the only thing you should do here is just say a poly over a poly, and that will probably be good enough. Not a great definition, but for our purposes, that's okay. After that, all we're going to do is talk about end behavior for a little bit. So if I ask you to describe the end behavior, let's call this function f, so f of x, and we had to describe its end behavior, we might start by saying what's the limit as x approaches infinity. That means look on the right side of the graph. Then we say look at function f of x. And we say, what is that doing? Well, to me, it seems like it is climbing at the end. So that means the y values are getting close to infinity. Okay, and we can do a better job of that when we actually know the equation of that function. Then we also want to look at the left side. So we say what's going on around negative infinity. And again, we have to label the graph so we know what we're looking at and where we're looking at it. This one seems to kind of be trailing off. It looks like it's going to a y value of 1 maybe. So this end behavior would be 1. And then just maybe some extra stuff since we have a little time here. Let's talk about that vertical asymptote at negative 2. If we want to use limit notation for that, I could do it, I'd have to still talk about it in two different ways. But I'm going to say as x approaches negative 2, but if I were to put a little plus symbol right here, that means I'm going to look at it coming from the positive side. So if I start coming at it from the positive side and I get really close to negative 2, all of a sudden the y values jump up to infinity. So we still need to say we're talking about f of x. But as we come from the right side and get close to negative 2, it's going to go to infinity. It's a gross looking infinity there. Let's see if I can, there, that's better. And on the flip side, if we say, let's look at what happens when we come from the left side, I'm going to say limit as x approaches negative 2, and now I put a little negative symbol there. That means what happens as I come from the left side and get close to negative 2, now the y values are getting really, really negative. So again, list the function, and that's going to equal negative infinity. So for the most part, we're going to be focusing on limit notation with end behavior, and that's going to help us eventually find horizontal asymptotes like we have over here. But we can also use it to describe vertical asymptotes, and there will be a couple questions related to that too. So just a note here, since we're talking about rational functions, if you find end behavior that gets a numeric value, so any sort of number, not infinity or negative infinity. That's basically what it's saying. If you get anything besides infinity or negative infinity, you're going to have the same thing on either side, whether you're getting really far on the right side or really far on the left side. It's going to be the same number. So if you found 1, you can guarantee it's going to be the other side will also be that number, as long as you know you're talking about a rational function. And then in general, we're going to have 3 categories for rational functions, and we have some examples to run through for those. So here are 3 pictures. I'm giving you the equations. We're just going to look at the pictures to find the end behavior here. They're all rational functions. If you look closely at graph A, it looks like it's trailing off right around on either side. It's getting really close to y values of 0. So if I wanted to use limit notation, I could just say the limit as x approaches. And since I know it has to be the same on either side, I can just say positive and negative infinity. This is f of x. It looks like the y values are equaling 0. For the second graph, now it's not around 0, but it does seem like it's trailing off. Now it's kind of trailing off right here, and that would be right around negative 4 on either side. So, again, I could write it the same way. Let's say, because again it's a rational function, I could just use this notation, plus or minus infinity. This is function g, and what is it doing on either side? It's getting close to negative 4. So both of these are number or numeric values. And because they were numeric values, they have to be the same on either side. But if I look at the third graph, now this one looks like it's climbing over here and it's decreasing over here. So infinity versus negative infinity, that doesn't follow that rule then, because we don't have numeric values for those answers. So now I would need to write it twice. So I'd say the limit as x approaches infinity for h of x this time equals infinity, right? It's going up on the right side, and the limit as x approaches negative infinity of h of x. So what are the y values doing on the left side? They're going down, so they're going to negative infinity. Now, we don't need a picture to figure this out. That's what the last little example here talks about. If you were to just have a polynomial, okay, all we're going to do is look at the first term of the polynomial, the leading degree and its coefficient, to figure out its end behavior. So since a rational function is a polynomial divided by a polynomial, we're going to look at the leading degrees and their coefficients in both numerator and denominator. We're going to look at that ratio, okay? And we have a kind of a set of rules for that. So if I were to look at the first one, x on top and then x squared on the bottom, I just look at those two parts. X over x squared, okay, it's going to get me it's going to reduce to 1 over x. So this is kind of like 1 over x. Okay, 1 over x, we hopefully know at this point, gets really close to 0 on both sides. And I can just use that as my model to kind of figure out what the answer for this would be. Okay, whatever this does, this has to do. For the second one, 4x cubed is the largest one over on the top. Negative x cubed is the largest on the bottom. And so if I were to actually do that division, I'd get y equals negative 4, right? The x cubes would cancel out, and I have 4 divided by negative 1, or just negative 4. And again, I can use this as my model for what the overall function is going to do on the ends. So this doesn't really tell me what's going on in the middle, it just tells me what's going to happen at the ends. This doesn't really tell me what's going to happen in the middle, just what's going to happen at the ends. Okay, and then our last example, I have x squared as the largest degree on the top, and 2x as the largest degree on the bottom. So this would get really close to x squared over 2x is like x over 2. You could also write that, let's see if I can squeeze this in here, 1/2 x. 1/2 x is just a line with a positive slope. So on the right side with positive slope, it should go up. That's what this tells us. And a line with a positive slope should be going down on the left side, so going down to negative infinity. So in general, yes, we have graphs that we can use, but we need to be able to figure out this end behavior just by looking at the equations too. And these 3 examples give you some clues towards that. Jot down questions, and we will see you in class.